Okay, where are we then? That's not what I wanted to show you. Right, okay, today we, by popular vote, yes, I got the docking working, which is cool. So by popular vote, it looks like we're going to be playing with a HUB75E panel, where we've got, this is a 64 by 64 pixel panel, and I think it's what's known as a 64th addressing, perhaps. Got my music a bit lower, let me turn that down quickly. There you go. Should bring the background down a bit. So I'm going to discard the fan controller, and this is actually a tiny FPGA BX, which I had planned to wire up, which I haven't done yet, and put onto the hub connector here, so that I could actually drive something with a reasonable frame buffer. I did do a project a while ago with the tiny FPGA, I think it was the A board, and that's got enough block RAM to do, I think it was RGB565 with 2 frame buffers, so you can do double buffering, but any more than that, and any more pixels than that, and it kind of blows the budget. So I was going to play with the BX at some point, but it's sat on my desk, or my shelf, sorry, for quite a long time, and I've not done anything with it. So let's just get rid of that. I'm not sure if anybody has seen, or if you guys are familiar with the HUB75E panel. So let's have a look at what that actually looks like in terms of the connections you need to make. We go to github.com I did a while ago, I did this, there we go, tiny FPGA A2, and I did a nice write-up for it as well, showing how we pack the RGB 565 data in, and a couple of calculations how to deal with the interfacing. But the important thing, or the interesting thing for today, is driving the LED matrix, I think, probably. No, maybe not. Look at this one. There we go, there's a pin out there. So this is the important one. And what this says, basically, is that we want to have... I'm not sure if... Should I cover how these are wired? Would you like to hear about that? How they function? It's going to be kind of important when we get to implementing this. Let me just sort out these wires as well. Yeah, okay. So what we have is, I'm going to go to draw.io because that's a fantastic site. I don't care. I just want to have a diagram, please. Change storage to side later. There we go. Draw.io is brilliant, yeah. So you have a panel, and you have a row of LEDs, and they are RGB LEDs, but I'm just going to draw one of them. So say these are all red LEDs. There's probably a good schematic somewhere I could just copy. And you have a number of rows, number of columns, and what you end up with is what is a shift register. So you load in a line, and then using a BCD decoder, I think it probably is called, you pick one of the rows to illuminate with that shifted data. Let's see if I can find a good schematic really quickly. Not going to be right, is it? This one kind of outlines it, probably. Oh dear, just give me the picture. Grab that then. No, that's wrong. Okay, let's stick with my drawing because I don't have something to hand. So you have a shift register, and let's draw that up here. And this has, you'll find that in this 64 by 64 panel here, there are actually a number of shift registers along the width of the panel, and each one might be, say, 16 bits. So you might end up with a number of shift registers chained on between each other. And that effectively just creates one really long shift register. And then you've got all of the pixels hung off that below. So I'm just going to draw this 1, 2, 3, 4, 5, 6, 7, 8. So let's pretend that this is an 8-bit shift register. Just stretch that out a bit. Oops. Like that. Draw that one. I'm just going to draw them straight onto each other. Or maybe I'll shift that one over. Oh, what am I doing? There we go. So the panel, oh sorry, the register here takes care of those LEDs. And it takes care of the entire column. So you actually get all of these linked up. I'm just going to draw that around the corner. Hopefully you kind of get the feel for it. I can't draw that around the corner. Fine. Anyway, all of the positive nodes of these LEDs gets linked up to the shift register. And then on the other side, you get a decoder, which takes care of all of the rows. So all of the negative sides of the LEDs come off to the decoder over here. Okay, hopefully that kind of makes sense. Following along. Now, the shift register, you have a serial clock in, you have the data in, and you have a latch in. All of these arrows are, of course, backwards again. Okay, so we got the clock, we got the data, and we've got the latch. And these take care of getting the data into the shift registers just like normal. So you clock in an entire row's worth using the clock pin, and on every rising edge or every falling edge, you move the data along one space. And then when you then strobe the latch pin, that data then all shifts into a lower register, which takes care of actually driving these LEDs. The row driver over here then has, I think it's probably 4 in this case, or actually 2 in this case, signals that come into it. And they give you the control over the row. So there's the A and the B signal, as it's called in HUB75 land. A and B. And so if we look at our binary world again, well not again, but if we look at binary, we've got 0, 0, 0, 1. The A and B values can have 0, 0, 0, 1, 1, 0, and 1, 1. And that then equates obviously to the decimal value of 0, 1, 2, and 3. Okay. And based on the value that you put into these A and B signals, it will pick one of these rows. So if you put 0, 0, you pick row 0. If you pick 0, 1, you pick row 1. So hopefully that kind of makes sense. Do feel free to stop me if it's missing detail or whatever. Now, to get the density up, what you find is that in this 64 by 64 panel, I think it's wired such that you have good. Thank you for confirming, Magus. So we have the full 64-bit shift register along the entire row, and then we have the actual display is then broken up into. I can't quite see that. There we go. So instead of being a full height, you actually break it up and think it's into halves. So you have a top half and a bottom half. And at one time, the clock and the latch signal go to a pair of chains of shift registers. And you have a data 1 and a data 2. Oops. I'll grab my data, put them too close together. There we go. So that'd be data 1. And then you have the data 2. These arrows have all gone crazy. Does that, and that does that. That'd be data 2. And these clock and latch signals are actually the same. So I could redraw that like this. That makes sense. And like that. Yep. And again, I think the A and B signals are shared as well. So you have this whole array is effectively 2 arrays, one on top of the other. Now looking at the pinout, the data 1 versus data 2 that I was talking about here, data 1 versus data 2, is effectively the red 1 and the red 2. But we also have shift registers for the green and blue as well. So you've got 6 shift register chains, and then you've got 4 bits to control the address of the row. Now, because this is 64 pixels high, we do 2 to the power of 4, we get 16, which is not going to do it. So we actually need another bit somewhere. So 2 to the power of 5 is 32, and 32 times 2 would be 64. So that would give us the addressing for the entire panel. So I think one of these grounds has probably been turned into a row or an address pin as well. Let's have a look for that. HUB75E. What's the latch in the context and why do you need it? Okay, if we let's redraw this quickly. I'm going to redraw the bottom one. I'm going to expand it out. What you end up with internally to the shift register is backwards arrows, is a number of there we go. So you have 2 registers effectively, and the shift between the top register and the bottom register is controlled by that latch. Oh, I've got V's all over the place now. That makes sense. And the fact that you have a latch now means that while you're clocking data into the shift register, you don't get artifacts on the screen. And so it means that you can be displaying effectively the previous row while you're putting data in for the next row. Not sure how else to explain it. But yeah, so when you're doing a display, you want to have the pixels on for as long as possible because that gives you more brightness. So it's some confirm instead of keep shifting and changing it. Like a refresh signal? Yeah, kind of. Let's follow a bit through the system, shall we? I'm going to turn all of these LEDs off. They're all red, okay? I'm going to turn them all off though. A and B is going to be 0, 0. So this line here is going to be hot or active. Let's make that nice bright pink or something. You can't quite see that very nicely. Let's make it bigger. There we go. Okay, so A and B are 0. All of the LEDs are off. All of the bits in the shift register are off as well. And what we want to do is turn on every other pixel, for example. So step 1 is to get the data into the shift register. So using the clock and the data, we can shift data in. On the rising edge of the clock, we get the first bit in, and say that's a 0. On the rising edge of the clock, we then sample data again, and everything shifts along. And we get a new bit in there. Okay. And then on the rising edge again, we shift everything along and we get the next bit. And we do that until we have the entire row done. I'm going to try and do this as clearly as I can. So there's the bit. We shift everything along and we add the new value to the left. Okay. So say we were to do that over and over again. We fill up the entire row of shift register like that. I've probably miscounted because there's too many on this column, but never mind. Now what we want to do is we want to light up the pixels. So we then strobe the latch signal, and all of these values then become present on the output pins. And so every other LED gets turned on. Boom. Okay. Now while that's happening, we can reset this whole process. The LEDs remain on, and we start clocking in the new data. So if we take the next row we're going to draw, we'll have the other bits, the other pixels turned on. So the first one's going to be a 1. Let's just ignore. Make that red. The first bit's going to be a 0. Okay. You clock that in. Yeah, cool. I don't want to go too deep if you're understanding, so if that's good with everyone, then I can just carry on. Yeah, so while we're clocking this in, those previous values are still present on the panel. And you keep going. And then finally, when you're ready, you turn this to the next row and you latch the pit signal, and this then all turns off, and the next row turns on. Grey again, turn that off, and this one on. Nice red. And you get the other bits turned on, okay? So I won't do it, but sounds like you understand. It's all to do with timings and brightness control, because the more time an LED is off, the darker the display will look. And that's not great for this kind of thing. So HUB75E pinout for a 6... Oh, it might actually be written on the back. But sadly, no, it's not. Right, what have we got? There we go. So this pinout gives us a clue. And I suspect that this pin 8, where I've got it drawn up here as a ground, is actually the E address. That makes sense. So maybe worth me grabbing this quickly. LED matrix, I think it is. I think in the documentation, we've then got the matrix module, or one of these. What's that called? That's called RGB LED matrix pinout. Pinout, there we go. If I grab a new one of these, we should be able to just load that schematic or that image straight in. There we go. So what we can do now is say that this pin 8 is purple and it's row 4. Okay. I'm going to take a copy of that, export as SVG, include the schematic or the diagram. Fixed. That's the one. Right, so Z project. Where are we going? Glasgow. I'm going to go to software, Applet, video. I'm going to make a HUB75E. I'm going to put the pinout in there just for now. It might not come with, but it'd be certainly useful to have there. So now the challenge is to wire that up to the Glasgow. We obviously need grounds, but they don't count to our pin count. I forgot to mention the output enable. That's an extra thing that we can talk about later. But we need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 pins. And we luckily have 16 pins on a Glasgow. So I'm going to lean forwards and wire this up just here. On these connectors, we've got one that comes into the panel, and then one that it shifts through the panel, and then it comes out the other side into what would be the next panel. Glasgow actually has 2 8-pin ports. It's got 8 pins and 8 grounds, as well as the voltage supply and the voltage sense as well. And then 2 disconnected pins, or not connected pins. Right, so I'm just going to sort through all of these wires, because not all of them are going to be useful for this. Might have to get some more out. In fact, a lot of these are not useful. No, okay. None of those. I've got 2 so far, and I need 15. Oh, that's okay. Feel free to ask questions. As ever, it's worth asking and learning. So one of the most useful things to get is just one of these packs or similar. Elegoo, they've done just a pack of DuPont wires, and they come in ribbons with pre-crimped ends. And you get these ones with receptacles on both ends, and you get this one with pins on both ends. I'm not sure if you can see that clearly. And then you get one with one of each, like that. Like that. There you go, you can see it over the black. Yeah, not many people. That's okay though. Maybe they'll join us later. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There we go. Pop them over there. Okay, let's have a look at this quickly. Oh, do you see that? I missed it earlier. It does actually say the pinout, which is very helpful. We have no real indication of which is in and which is out, I don't think. But we do have the arrows. Now these arrows, I think, point to the top of the panel. Where's the other one? It's there. And I think these arrows point to the direction of data travel. So I'm going to go with it goes in here and it comes out here. And because we're only doing one panel, I don't care about the output side. Obviously, you don't want to drive data into the output side as well. I would love to zoom. Unfortunately, my camera's not got autofocus, so it's a bit of a pain to deal with. And how do we get? There we go. Bit of a pain to deal with. There you go. Can you see that okay? So that shows the, I think, input signals with their pinout drawn on the silk, which I missed earlier. I was expecting them to be next to each pin. Cool. Redo the focus quickly. That looks okay, I think. Okay, lean forwards time. Have we got enough? Oh, we haven't got enough to do red, green, blue colours for the red, green, blue signals, but that's kind of alright, we can deal with that. Just need to keep a note of it in our mind or on paper even. Here's red, orange, yellow, green, blue, purple. And I think I'm going to use those for the colours. So start with red. Red goes red. Richard of red, green. York, blue, yellow, sorry. Richard of York. Green is going to be the next red, so I know it's green, but it's going in the next red. Okay, battle, indigo, violet. So there we go, just like that. And then we've got some addressing. So we've got 5 address bits. Don't rip them all off. They're a bit of a pain to deal with if you don't do that. I'm going to put the colours on port A. So let's just go sequentially. Now on the Glasgow, the data signals are on the inside and the ground is on the outside, and then 0 on this end. So skip 1 for the vsense, and then we've got 0. There we go. So Richard of York, etc., etc. Richard of, oh, I missed out the yellow, of course. They're cool little panels, actually. Let me just concentrate on the colour order, because otherwise I'll get it wrong. Yeah, they are cool little panels, and they are really quite bright if you drive them correctly and carefully. There we go. We've got 2 pins left over, and because we're 14 out of 16, I'm going to leave them, I think, blank and put all the other signals on the other side. We've got purple, we've got black. I think I'm going to make black the ground, just to make common ground. Purple, we've got a brown, grey, we've got 2 greys, 2 whites, and a blue. And a yellow. So I'm going to go for, I think E. Actually, let's go A, B, C. So A is grey. A is grey, that's going to go in pin 0 on port B. Yeah, the Glasgow's got 2 8-bit ports. So this is port A and this is port B. And each of them has each of them has 8 digital I/O signals that you can wire up to things, as well as independent voltage output and voltage sense as well, so you can use it as an ADC. And the Rev C2 of Glasgow, which is what's going to go into the crowd supply campaign, is actually able to measure voltages up to about 36 volts, I think, which is kind of cool, to be honest. Sort of not quite multimeter land, but it's certainly something that you'll have to try pretty hard to blow up, if you put it that way. A, B, C. This could turn into a board as well, couldn't it? A, B, C, D. Hey, Isden. We're playing with HUB75. I saw your messages. No worries for being late. You're very busy at the moment. I appreciate it. Is that a challenge? What's the challenge there? Sorry. Oh, there's no worries. I was just saying that this could potentially even become a PCB because it's a bit of a bum to wire up. So there's all the address lines. We've now got to do clock, latch, and the output enable. I think I'll just do them in that order. I'll blow stuff up over 36 volts. Well, I mean, if you've got 36 volts handy, then, or over 36 volts handy, then, yeah, bit of an awkward one to explain, wouldn't it? Passive adapter, yeah, I think so. That would make it really nice, I think. We got, that's the clock, latch, and finally the output enable. And then the grounds seem to be labeled N here. I'm pretty sure that's ground. So I will just check it quickly. I was just showing this off, Esden. I used the tiny FPGA BX, or AX, sorry, a while ago to do a proper frame buffered RGB 565 display. And then I got a BX, and it's in this state, and it's stayed there for perhaps a year. The LED panel PMOD, what is that sort of the starting point, you mean? Oh, cool, okay. Is that for the different scan rates and things? In you go. Right, you can't quite see from there, apologies. I'm just going to wire up the ground. Right, there we go. Now, I've prepared the power for this. It's quite a chunky connector, and these can draw quite a lot of power. So there are actually 2 wires that come in, and it goes into this big chunky connector here. And that runs off to my bench power supply, so we'll turn that on when we're ready. We'll turn that over now and plug it in. There we go. So is this going to work? About. I'll leave that in the corner there. Oh, okay. I hadn't realised there are other standards. I've been on the periphery of this a bit. So here's the pinout, which I have redrawn from previously. I'm just going to translate the pins from the pinout onto what the Glasgow connection is. So that would be port A0. Do it nicely. all of those again. Right, port A1, port A2. That's nothing for now, at least. There's no reason it can't be ground. Port A3, 4, 5. This is then port B0, port B1, etc. Port B4, and then we've got the others here. And that one is actually connected to ground. Oh yeah, agreed. In terms of flexibility, if we can do all of the other types, that'd be brilliant. I'm just going to highlight the A's so that that's nice and clear. Let's make it green, and all of the B's so that's nice and clear as purple. There you go. What happens if I do save, download, pop it there? There we go. Okay, I'm going to keep that on my other screen. I don't think we should need to refer to it too much, but once we've got the beginning of the code for the applet written out, it should just all sort of disappear for us, which is nice. Right. Okay. Oops. Okay. Okay. So there we go. Let's get. Well, let's just use this window, and we are going to fall into software Glasgow Applet video, and we're going to make the HUB75 directory. Branch created a bit. We're halfway there. I'm going to take inspiration from the Vga output module, because that's one I converted earlier to endMyGen. Ooh, no, it looks like that one hasn't been merged yet. So let's go for interface UART. We can always come back when we need some other more specific things. Yeah, that was cool. Well done for getting that working, by the way. It's nice to see things like that happening. I never quite managed to get my panel hooked up to a video source, unfortunately. I got static frames, which I was sending over a UART, which I'd implemented in the FPGA, on the tiny FPGA board. So it wasn't particularly fast, but it did the job. Loading one line by line at a time. I'm going to call it HUB75. I don't know about the other standards, but we can talk about that in the pull request when we get there. I'm going to fill the description in later, and that's going to have things like the pinouts and stuff in there as well. Ah, very good. Got red one, green. This is where typing is going to fail me. And then we've got, I'm going to call them A0 for address. A3, 0, 1, 2, 3, and A4. And then we've got clock, latch, and not OE, which I'm just going to leave without stylized inversion. Sorry, what am I doing? I want to group these into red, green, blue 1, and then red, green, blue 2, address 5. There we go. That looks good. What of these do we actually want? I think let's just do that. I want to see how it deals with those the build arguments quickly. I'm not sure if we can just run this already. We need to add our module into, or applet, sorry. Is it applets? Where is it? Oh, all. And we're going to find a video, add ourselves to the bottom. HUB75, it should probably be HUB75 output. HUB75 output applet A, B, C, D, E, F, G, H. Go to the top. Let's rename that quickly. Oh, do any of the imports, how silly. Oh, it looks like the UART one's not nMygen either yet. There's got to be one in here which is merged. The PS2, the audio DAC, the UART. Oh no, UART, you got part of the UART already in. Okay. Let's have a look at the I2C initiator. The merge pull request I think is in progress still. I need to look into chasing that along. I think White Co-op needed a bit of time to focus on other projects, and I equally started focusing on other projects and it got left behind. Come on, move. Was that hey you there at me? I'm here. Or was that at the PR? Yeah. What are we importing from ... Oh, is that the is that the main applet stuff? Okay, that's fine. All right, let's see if that runs now. Hopefully it'll give us the HUB75. It does. Doesn't say video HUB75 output though, so let's fix that up. Video HUB75 output. Now we want to grab it and see what the help's going to come out as. Okay, so RGB, and then it's put A2 on pin 6, which I don't think I wanted to do. I'm going to have to shuffle them all along if I do that. There's nothing wrong with that, but I might look to see if there's a nice way to deal with that. This is the I2C, and it just plops the pins wherever. Have a quick rummage, and we can always defer and move the pins. Oh, the desk, yeah, sure. How's that? Hold the Glasgow in position. Ready for a vanity shot? Not quite right, is it? My Pokeball golf ball just in the corner there. No problem. Yes, right. We were trying to add pin arguments, weren't we? So grep to right. Okay. So none of these actually have the ability to say which pin you want it to be. If I do it again, we'll get the access in it. Here we go. Default none, parser name. What line was that? Oops, no, don't do that. No, sorry about that, everybody. I'll be here for a while. Line 26. Oh. That was unexpected. Probably going to be that, isn't it? Yes. There we go. Pin num. I think I might be able to put default in as a number. It's not none, required is false, no. Oh, okay, default. Let's just try that quickly. So if I make this into what are we going to do about that then? We want to do red 1, default 0, and then I can probably get rid of it from here. Oops. Does that still work? Yeah, it does. Oh, we got two on pin 0 now. Never mind. Let's do red, green, blue. Red, green, blue. On 1, 2, 3, like that. And then we've got the second set on 3, 4, 5. Is that going to come through? Yes, cool. And then we do A0 is going to be, so because we're addressing pins RIP, question mark? Not following you there, sorry. Because we're using both ports, it goes 0 to 7, and then on the next port it goes 8 to 15. So this is going to be 8. A, B, 2, 1, 0, 1, 2, 3, 4. That's going to get 8, 9, 10, 11, 12. Oh yeah, I had previously copied quite a bunch of text in tmux, and let's just copy something small, I guess. And then I pasted it by mistake because I fumbled the key press, and so I just spent forever pasting into my console, which was not ideal, I have to admit. 13, 14, 15, and these are the clock, the latch, let's spell out completely, and I'm going to just call it OE, that's fine. I don't think these pins are actually used anywhere else. What does that give us? 5, 6, 7 are missing, which is good, that's how we've wired it up. 8, 9, 10, 11, 12, 13, 14, 15, cool. At some point we will want to do things like clock speeds and scan rates, so what I was talking about earlier in terms of how many lines you have per half, how many address bits you have, etc. We'll want to tidy that up, but let's just work with this screen and get something working for now. This is probably Okay, I probably did want to keep that then. R1. Make it more generic, exactly. Yeah. So once we have something that works, we can make it nice. So HUB75 output sub-target. Like pads, spell right. iFace get pads, args, pins, self pins. I don't think we need the FIFOs at all. And the period there is just going to be to deal with clock speeds and stuff, so we don't really care about that right now. I could have done null pins or none pins. I think I'll actually come back to this off stream, and I'll make it into a list of tuples with the pin name and the pin number, so that we can pull out the name and number here. But then in this situation, we just want all the names. And that would be quite nice. A list of name number tuples. Yeah. But I won't bore you with that. I can do that later. Don't care about the pulls, so that's actually something we can probably not implement. What do we need to do here? I think we just need these ones, don't we? You want to scream to put a semicolon on the end of the line? Yeah, I have to admit, having done I don't know, about a month or so of working with Python, I then came back to do some C, and I kept doing indentation for context and missing off the semicolons. It's funny how your brain works like that. I like Python, it's good though. Okay, let's just look at the VGA. Because part of this is going to be pretty similar. There we go. So there's the pinouts that I was going to fix up later. All the porches. Clock constraints, don't care about that. If test pattern, yes, we do want test pattern. So that's actually something that is put in at the build step. So I'll come back to that. There was something I had to do in the PR to make this, convert this to nmygen. Right, there we go. We just need to return, await, device demultiplexer, claim interface, self, mux interface, args, nothing else. Okay. Okay. Tell you what, let's have a look at the VGA. That's how it's, I never quite remember. Yes. So this is the VGA file which has been converted to nmygen instead of using ye olde mygen. And here we go, here's the pix generator that I was talking about. So let's actually do that as well, because we're going to need something similar to generate pixel values. nmygen is a reimagination of mygen, which is the original or the older, I don't know what to call it, the HDL, which is kind of, HDL being hardware description language, which is, what is nmygen? you write Python to describe your hardware, and it then generates the underlying, I think, Verilog from that, and then builds it. So nMygen is just a reimagination of Mygen, basically. I almost want to call it a meta language. I'm not sure if there's going to be something on the website. We actually want White Quark's one as well. And there we go. It's a Python toolbox for building complex digital hardware. I'll put it in the chat. You can go and have a look-see. I would call it a meta language in that it's not the Verilog or the VHDL or whatever that it's actually writing or translating into underneath, but it is, you are still describing your intent in Python. Okay. No. That was a direct copy. And in here we just get the pads. Not sure if you saw my previous stream on nMygen, I guess, where I covered kind of doing a lot of the conversion from Mygen to nMygen. But fundamentally, you have this module which you then do stuff to describe your logic. You have the comb, how you want to pronounce it, which is short for combinational. And in here you do you can write expressions which are always true, and they're effectively wired up with raw logic gates. So there's no clocking or anything. If you write that one signal is equal to, in this case we got the horizontal strobe is equal to the horizontal counter equal the horizontal active. So if that condition is true, the horizontal strobe immediately just becomes a true value. So that's combinational. And then you also have what's typically sync, which is synchronous. But in this situation, we're actually using a different clock domain, PIX. And in the sync, or in this case, the PIX clock domain, everything is clocked and is in sequence with each other. So at this point, if these two conditions are true, then the pixel will the pixel clock domain gets this extra thing which happens on the clock edge. So the vertical counter becomes set to 0. That was really brief. You'll probably start to pick it up more as like going, this is FPGA programming. Yeah, this is logic. It's not procedural programming like normal Python, C, etc. We're actually describing combinational logic and sequential logic that then gets converted in, I think, into Verilog, and then finally into the bit stream, which is put onto the FPGA. And the FPGA is the big part of Glasgow that we've got here. I'm sure you'll pick up how it works as we progress through this, though. Cool. Glad to hear it's making sense. Right, we need to define some things. So we've got the address pins individually, and there are 5 of them. So we need the address or the row, and it's going to be a signal with 5 bits in it. Then at reset or at the startup, that gets set to a default value of 00000 or 5 zeros or whatever that might be. I'm not sure if I overcounted. And we can then influence that on a set basis. So initially, we're not going to deal with gradients or color, brightness control or anything. We're just going to do on or off, just to make it really simple and hopefully get something on the screen. So I'm just going to call them A for this first state. We can name them once we kind of understand what's going on. The first step is to shift out. Let's just go for everything on. So we need to shift out columns. So column is signal, and we're going to use a range here to say that it's 60. It's got to be able to store 64 as a value. And I think actually that's 0 to 63. So in the first case, we need to set m.d.sync col equals 0, say, and then m.next equals b. And that's going to advance us onto the next state in the state machine. In here, we then want to start shifting out each of the pixels in that row. Yep, there you go, state machine. So here we need to make a little while loop. I'm actually going to say 64 plus 1 just to make sure that we actually can count and we don't loop. I think we should be fine. This is one of those things that always throws me in terms of zero-based counting. So with m.if, so we're going to say if col is not equal to 63, then what we want to do is m.d.sync, the one-off thing, yeah, exactly. Self.pads.r.equal r1.equal r1. We can do that for each of the other pads. So RGB, and then these are going to be 2s. So set them all high. And we now need a clock. So we can do. First pattern is going to be all on. We're just going to do a simple, just white, really bright. See what happens. Dig. I'm going to actually double this times 2 and just implement the clock in a really nasty way. I'm also going to put all of these into here. This is just really, really hacky for the beginning. So if with what we're going for cold is not equal to, hey Omni Technomancer, thanks for joining. We are playing with the HUB75 panel. The description is not accurate. We're not playing with the fan controller. I apologize for not updating it. Let me do that quickly. Actually, no, I won't do that quickly. Everyone can see, hopefully. So we're playing with the HUB75 panel with Glasgow to try and get just a test pattern on there. Trying to figure out as well what's going on. So if column equals 0, let's do top-down counting. M.next equals C. Column equals 64. All LEDs off is a pattern. I mean, yeah, it's not very functional at the moment. I mean, we can't do anything else with it. So this should give us 64 clocks and then advance onto state C. It's not very well designed yet, this, but let's just make it run. In state C, we'll then have a counter, I think. And I'll just make it 64 again. I actually wanted that to be 64 times 2. State names are not meaningful yet. I just want to kind of get a feel for how this might work. I did a previous write-up about this, which I was talking about earlier. And let me have a look at this one. Driving the module. So, oh, there's a nice diagram I could have shown you. Sorry. There we go. So because of the way it works, you get the ability to send send the next line while the previous line is still being displayed. And then you change the timing to get the brightness control. So it's all a bit sort of all at once. And to just get things working, I want to be very non-optimized and do things one by one, I think. And I'll come back and name the names, or name the states. I'm actually going to move this into here on combinational logic, I think. Oh, I see. Yes, the row address pins are labeled A, B, C, D, and E as well on this panel. So no, these names aren't related to that, unfortunately. I could let's go for reset, I think. Row shift, I guess. And then show or delay. Let's go for delay. How's that? Is it better? Let's go for count equals 32 count. Awesome. Count. If count's not equal to 0, then we want to decrement it. And if we have reached 0, and dot next equals reset. Come back to the top. Now at this point in the reset, we probably shouldn't be calling that reset anymore. We want to call it row advance, I guess. Row advance or row inc or something like that, where we do m.d.sync. Actually, we can put that down here. Let's do that. Row dot equals row plus 1. Let's just do that. Okay. Reset is probably the wrong phrase for it, but that should be okay. Now we have a signal. We have the output enable signal, and we're going to set that in m.d.combinational. And we're going to set it to no, let's not do that. Let's do it here. We're going to set self pads OE dot equals 1. It's actually inverted logic, so we probably want to put it here as 1. I was going to say that it's only going to be 0 when we're in the delay state, but maybe I will come back to that one when I can remember what it was called. Before the delay, we actually need a latch as well, so we can have m.d.combinational. Hopefully, we've got enough speed in that part to latch it. No, let's put that in here. Self.pads.latch. So I think there's positive going latch, I think. Just review from here. So the latch is a positive going latch, and the output enable is a negative or inverted signal. That might even make it work. What are we going to do with this? We are going to start at the beginning. We turn off the outputs, set the column to 64 times 2. Then we move on to the row shift, at which point we still keep the outputs off. We set the RGB for both halves of the panel to just 111, and that means it's going to be whitish. The column is going to be 0. When the column is 0, we are going to advance. So we advance the delay. So while it's still counting down, we're going to clock the output with the least significant bit. So that should wiggle the clock for us. Decrement it, and then we pop into the delay. At this point, we're going to count for 32 clocks and then move on. I suspect we are going to be running quite fast here, but I think let's just see what happens. Does it actually run? Minus V, I think, is going to be 5 volts for these. And it's probably going to ask me to choose a serial number. And let me just check which was used here. This was 4926. 1 gigahertz. I think that might make it quite unhappy, to be honest. Right, here we go. I need to turn the power supply on as well. Oh, no attribute pin underscore lat in line 88. Oh, latch. Is that what we're after? Yes. Just rename that quickly. Line 20. Self pads OE. Oh, we've got to set all of these to outputs. I forgot about that. Pad.oe equals 1. I think that'll be good. Let's just print the pad out here and see what it comes up with. Why is that not working out? Pad is not iterable. Oh, I thought it was. Pads object. We've referred to something else which uses the pads. Is it a dict-like object maybe? Pads. Self pads. Think. Okay. So RGB, and we're just setting the output enable pin for these pads now, so that so the signal actually comes out of the FPGA instead of trying to bring it in. We've got the address 0, 1, 2, 3, 4, 5. 1, 2, 3, 4, not 5, sorry. And then we've got the, I can't remember what they're called now. Clock, lat, and OE. OEOE equals 1. Is that going to work? Maybe. It's probably going to complain again. Doesn't have an R1. What's the problem here then? I think when we asked it to get the pads. Oh, no. Self pins should be a tuple just like that, which it is. Dig into that function quickly. I think that's going to be a stub. No, it's not. The get pad takes the arguments and the pins. And we have given it the arguments and the pins. That's fine. That looks okay too. Yeah, we've got all of those. And num equals. Okay. What's going on here? Let's check what this is doing again. iFace get pads, self pins. Self pins is just a tuple like that. We've added each argument in the same way that they're doing it, but slightly different. Could this need to be true? Sorry about this, everybody. No. Don't think that'll do it, but let's have a go. Nope. Oh, grr. Numbers truthy. Yeah, they are truthy, but if I do help, these numbers come out here. And that's kind of what I wanted. So the reason is we've connected up the RGB for column or half 1 and then RGB for half 2 to port A. And then we've got the address pins and clock latch output enable on port B. So we've missed 6 and 7, which all seems to be okay. Pin R1. I don't quite see what I'm doing wrong here. Oh, I know exactly what is it. We've got to have an underscore T on these. Oops. Minus V5. Yeah, there we go. Oh, I'm sorry. That's annoying. Let me do... So we've got the output enable. Just highlight pads quickly so I don't miss any. Not that one. But why? I don't know. Just is. Oh, these now need the O's on them as well, don't they? There we go. No attribute latch t. It's called lat, not latch. L-A-T. Yeah, that's fine. That's better. There we go. Oh, we got some red, which is actually quite unexpected. The reason it's unexpected is because the power supply isn't even on yet. So Glasgow is clearly powering this for us. Not sure how well you can see that from there. I might turn off. Quick edits in Vim are great. I was about to write some regex just now, but I decided against it because it would probably take a bit longer. There we go. Can you see that a bit better? So let's turn the Glasgow's voltage AV0, turn that off. Voltage. What? Yeah, voltage. Oh, I've not got serial number in there. Just enough power for red, yeah. Right, let's get the power supply going. Now I'm pretty sure this is 5 volts. I'm going to give it 100 milliamps to begin with. And it's drawing all of that. Let's give it 200 milliamps. Does it actually come up? Yeah, that's better. Okay. So the quiescent current, just watching the power supply, is about 120 milliamps, which is a bit shiny. Come on, live the power supply. Yeah, it's awesome. I'm lazy, so I don't like to get up and go over to the power supply. So we can monitor it, keep it down there, just make sure nothing's going crazy. It is actually a fairly cheap 10mA/co-rad power supply. I highly recommend them if you're in the market. They are nice and solid. I've also got some more serious TDK Lambda ones, but they don't get much usage at the moment because this one just runs. It's over on my other desk. I'm quite lucky. I've got a computer, like software desk, and then over there I've got an electronics desk. So the scope and power supply and everything's over there. But what's this going to do? Nothing. Power usage is up to 170 milliamps, but still nothing on the output. And that can be for a number of reasons. Voltage 0. Power drops again. Stop it! I'm sorry. Right, what have we got going then? We've set all of these to outputs. We have a reset phase which will put the output enable to high to turn off the LEDs. It will start the column address at 128. Let's write that in. It's actually just USB, and the power supply comes with a sort of a USB connection, and you can talk effectively over a serial port and give it commands to turn the output on or off, set the current and voltage, set points, etc. So it's pretty easy to deal with. Right, we need to shift out a row. So we give them all high values. Let's go if column is not 0. Swap this around just so it's a bit easier to reason about. Excuse me, 128 is the starting value. Oh, I hate this new calculator, 128. And that has a low bit of 0. So it's going to start with a clock of 0, and then it's going to go 1, 0, 1, 0 all the way through until it gets to 0 again. And when it is 0, it's going to fall through into the next. So I think that's okay. I suspect the latch. Oh, we've got a latch in here? Oh, no latch. Oh, here's the latch. So the latch goes up. I think it needs to come down again. Okay. Let's put that in as a with m.state delay latch. So that goes up. Delay show. And that then comes down again. Combination of output of the output enable goes low, and then it counts for a period. I think we also need to do a count in here for probably 32. Let's just use 32 as a number. That then goes to delay show like that. Okay. Don't want that one. Okay. What are the bets that this is going to go bright white? Not good. It's still going to go red if we turn everything off. Yes. Oh, we got something if I turn the power supply on while it's running. Okay. These values could be too small. What is a counter? Flash test. Let's just do range. Let's do a 32-bit value there, so we can just make it huge. I think also we're probably going to need to slow down this clock. If count is not 0. Let's have a look at these numbers actually as well. So we've got a 48 megahertz clock, 48th, and we want probably, let's go for a 10 megahertz, like that. So we need a divisor of 4.8. So divisor of 32 is going to be 1.5 megahertz clock. That's plenty. We don't need to go much further than that, I don't think. So here we're going to loop. Around. We're going to do a clock wiggle, followed by a clock wiggle, followed by a clock wiggle, but slightly slower than we were doing it just now. Then we're going to delay the latch for a period. Then we're going to delay the show for a period, and then we're going to move on to the next row. Oh, thank you, Esden. If you're saying you tweeted about this, it's very kind. Ooh, nothing. Right, this might be time for, let's go quickly. Been having a bit of play with A. Zonenberg's scope HAL client, or whatever it's called. That's pretty cool, to be honest. I don't have a Mastodon account, but please feel free to message the Mastodon people. Okay. We go for something suitable like that. I think. And cursor's off. Oops. this going to work? Can you see the scope? Yes. Look at that. Okay, what have we got? This is currently running. That doesn't look like much, does it? Let's turn the trigger off. Oh, hey Greg. Thank you for joining. Hope this is at least somewhat interesting. We're currently trying to play with a HUB75 panel on Glasgow. There's something on 5 and something on 6 as well. All right. So we have a look at 5 and 6. They are. Oh, I'll put it here. It is. No, where's it gone? Ah, I've lost it. There you go. So port B, 5 and 6 are the pixel clock and the row latch, which looks promising. But I think the major issue is perhaps that. Put you back on the scope. Perhaps that. So we need to zoom in on that. 5 and 6. 7 is the output enable, so that is actually working. But the address lines are all just low, so I think we probably need to deal with that. Matter of urgency. Let's come into this, see what we go for. Oh, unexpected. I should really have a better setup for this, shouldn't I? Measure the peak-to-peak frequency, that's fine, yeah. Yes, I do remember that from when I first got things going. Oh, hang on, I'm not triggering. That's probably why it looks so grubby. I'm triggering back on again now that we found something. So 5 is there, and 6 is there. Probably far too close now. Trigger point. Oh, let's go for more like 2.5, 3 volts. What's happened here then? Oh, I stopped it, did I? No, that should be all right. Oh, where's it gone? This might be something calling for a... I got some of these. I'm so excited. I can show people who might be interested. Let's see if I can show you my face. There you go. What are these called? These are the Sense Peak probes with a nice wiggly arm and a magnetic base. They do actually a really nice job. The arm it's not nearly rigid enough to support its own weight. So that's kind of a bit of a surprise for me. But yeah, the needle's spring-loaded. It's quite nice, and you can generally get it to balance just about where you want it, which is pretty cool, to be honest. But I digress. That's not what we're looking at. We're trying to look at this. That's my finger. That's pin 5. That's pin 6. That's pin 7. Has 5 gone quiet then? Oh no, there it is. Maybe I just wasn't breaking through. Right. I am not well set up for scope while streaming, I don't think, am I? Yeah, so I've got the sort of the logic analyzer probes, or the multimeter probes, so I think they were referred to in the sales. And I haven't actually used those, but I have used the 200 megahertz probes that I got, and they seem pretty nice actually. They're not perfect, but I don't think they would be. And you can see, a lot of the time a scope isn't for precise measurements, it's for getting visibility on what's going on, and for that it's plenty. And I've got 4 of them, so you can put needles on wherever you need, and yeah, brilliant. I would recommend them, although I haven't had loads of use with them yet. This is really puzzling me. Why are we getting... Oh, sorry, I've been doing something with funny triggers earlier today. Let me... Typical, isn't it? There you go. That's the one. That's saying 700 kilohertz, which is about half of what we were expecting by calculation, which is perfect-ish, I think. Okay, so 5. Ooh. If I short those two, we get some colour on the panel. Look at that. Don't want to short those too much though. So 5 is the pixel clock, I think it was. And that gets a nice 720 kilohertz, which is kind of what we expected. 6 is, again, a single pulse at same kind of width. And I will count maybe. I think that all looks okay. The issue now, I think, is that actually we're not changing the row where we should be. Let's come back to that. I do need a really proper remote control for my scope. Yeah, I've not really used it from this desk much before. Usually it's sort of really hands-on setup, and then you come back here and you tweak some software, reload it, whatever. Okay, let's go in for 30 megahertz then. We've got a 48 megahertz clock, so maybe let's just go for a divisor of 3, which will give us... Let's go for 3. What will that be? Got another calculator open now, so that divided by 3 divided by 2 will be about 8 megahertz. I think that's plenty for right now. If we get it working, then we can always increase it. Still need 128 of those. So that's good. Let's rerun that applet. Oh, flash again. I think that was exactly the issue, that we're not changing the address. There we go. Sorry, I'll show you the scope again. That's coming in at 6-ish megahertz. Can't remember what we said now. 48. E6 divided by 3 divided by 2 is 8-ish, so not too far off. Zoom in a bit now that we're going a bit faster. Okay. Right, so our rows aren't happening, and I think I might know why the rows aren't happening. Because we are setting the signal, but we're not actually putting that signal onto any of the pins. So let's do that just here. m.d.com. There's going to be a better way to do this, but a0t.o.equals row 0. If anybody would like to share the better ways, concatenating a 4, 3, 2, 1, etc. Can't bother to look it up right now. Fingers crossed. Oh, look at that! Oh, it's exciting. Can you even see? Oh, there we go. The camera looks a bit delayed. I can be shifting the data while I'm exposing the row. Just to keep things simple, I think let's avoid doing that. Thank you. So that's white. Red, green, blue for the top half versus bottom half, etc. is going to be simple. So let's just do red on the top and blue on the bottom, just to prove the point. That's not what I meant to edit though. I meant to edit the data here. So red, green, there we go. And this should chop it in half, approximately like that. There you go. That gives us the orientation of the panel, with the red bit being the top. The top is here. Oh, my Raspberry Pi camera's gone really slow. Let me just start that again. While we're waiting for that to come back, I will work on the next thing. So we've got the row, we've got the columns. We can start getting a test pattern in here, and we can probably start making this quicker. I don't know what the parts are. They're probably some fairly cheap something from somewhere with no accessible data sheet. So if we just go for 25 megahertz, we need 1.92. So let's go divide by 2. On the pixel clock, we actually don't need to do any of that because we are already divided by 2 effectively. On the latch, or for the delay, let's go 1 and 1. And this, I think, will probably make it a bit brighter. Else if without proceeding if. Maybe. No, not much brighter, but it should be more stable. We can watch the scope again. Let's have a look at that. So if we look at the pixel clock, ooh, that's now 24 megahertz. I think that's good. Let's leave that there. I'm not sure why the overhead camera has not come back yet. Let me just poke at that again, sorry. Okay, so we've got top, bottom. I think maybe now we need to get a test pattern on there, which means we need to generate the RGB values from possibly the column. So I think if we go for column, let's go for 3, 4, 5 maybe. How many columns have we got? We've got loads of columns. Let's go 5, 6, or 5. Yeah, 4, 5, 6. 4, 5, 6. And then actually we could go column 7, 8, 9 on the next one. And that will give us a nice sort of different set of color bars. How many bits in 64? Actually, it's 128, isn't it? 128 is only 8 bits. Right, well, let's resolve that quickly. There we go. Ding, 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 ta-da! Oh, you can't see it still. I'm sorry, everybody. That's a real letdown, isn't it? If I do this, does that help? I might need to turn the camera all the way off and on again. What can I do instead? That's really disappointing. I want to show you this, but my wires aren't going to be nearly long enough, I don't think. Oh, just about in shot. There you go. Yay! Apart from you probably can't see it because of being washed out by everything else. Let me turn that off and on again quickly. Okay, I think it's coming back. The pattern, right, so the pattern, we don't probably want that. It's not the best pattern. We might look at increasing the brightness by, as Esden was saying, you can display one row while you're clocking out the next row. I think that'd be quite a good thing to do. I don't really feel the inclination right now to get this working with variable brightness. So have a look at my write-up from the previous effort I did. Here you go, you can have the least significant bit for 1 millisecond, for example, and then the next significant bit for 2 milliseconds and then 4 milliseconds. And this then gives you the ability to put the brightness at varying levels instead of just on and off. There are probably other schemes to do this, which might be something that Esden and or Greg can comment on, given their experience with these panels. Maybe sort of a nicer way of doing it, but that's the way I did it last time, at least. So let's, oh, actually, we can probably just double the brightness by doing this, can't we? TNT's the guru, is he? Okay, watch out for that. So if we double the brightness, so in terms of shifting the row out, we can actually keep the output enable on during the next row shift, and it's just a matter of changing that bit there. The reset can probably take a 0 as well. I might get a little tiny bit of garbage on the very first line, but I don't really care about that right now. Oh, wowie. Look at that. Straight up to 3 volts. And that's interesting as well, because we've got a bit of a color shift on there. Okay, was unexpected. No, I know, I'm really annoyed. I'm trying to let you see the desk. Come on, Raspberry Pi camera, please work. It is brighter now, but if I describe it to you, we've got a half, oh, there you go. So we're drawing a good 4.3 amps now. We've got half white and half yellow. It's getting a little bit warm actually. Let me grab this panel I've got. I've got this diffusing sheet I was using previously. Does that help? Maybe a bit. That's probably too much now, isn't it? Get my glass out of the way. There you go. You can kind of see the yellow maybe. Maybe. No. Oof. The other thing I could potentially do is actually turn down the aperture on this camera, which might do quite a good job. Auto gain there, of course. When you have 100% light efficiency, I don't follow that, sorry. Are you referring to this, this one here? In terms of the shift time being longer than the shortest lightness or brightness period, which means that you can't get the row on, you know, if you have an FF value for that row, then you can't get 100% light for that row still. Yeah. That was quite frustrating. Obviously, once you get past the first few bits, then you start to get longer and longer durations, and the shifting while you're clocking, or sorry, displaying while you're clocking the next line in, or the next value for that line, means you can get some nice things happening. I wasn't showing my screen there. This is what the graph or the chart I was referring to. Anyway, let's. So at the moment we've got this yellow half and a white half, which is not what we want. We want to keep that pattern in there with the test pattern that we had earlier. There we go. Now the reset, if we put that reset output enable to on, we get yellow, which is interesting. I wonder if that's an artifact of everything changing at once or something like that. I don't quite know. Never mind. We can actually also just go straight for that. Let's do that later. After hum. Oh, that could be. It could be the noise of the power supply. Actually, shall I try turning that off and see if it gets better? Is that any better in terms of hum? I put some gates and things on the audio stream, so it could be that it was struggling to disable my audio again. Yeah, exactly. Power supply goes a bit worry when you're drawing 10 watts or so, which is, oh yeah, it doesn't feel like it's that much, but it's linear and everything, so maybe it needs a fast fan. Cool, good to know, thank you. Right, let us, okay, so the the VGA test pattern. Let's just look for that quickly. Is that going to bring me up? No, don't be silly. Not nearly popular enough for that. Let me just grab that video quickly. The test pattern is kind of is blocks. Let's change it. Yeah, go for it. Help me out. So in terms of yeah, this one. Actually, I wanted to do that. No thanks. Oof. Right. Okay. We skip along. We have the monitor. Where is it? It'll be around there somewhere. Yeah, there it is. I bring it up to the camera at some point. And you can just about see it in the background down in the corner there. Go to the beginning. Oh, there's bigger. There, yeah. Perfect. So I think this is the kind of pattern which would be nice to recreate here. And the way that's done is by taking into consideration both the horizontal position and the vertical position. So we can look at the VGA test pattern to get a feel for how that's generated. And there it is here. So we take the horizontal position plus the vertical position, and that gives us the pixel value for the red, green, blue. Now, this is a little bit fiddly because the vertical position, because we're drawing the panel in two halves, the vertical position for the top one is going to be 0 onwards, and the vertical position for the second one is going to be 32 onwards. But that's okay, I think we can deal with that. So, what do? I'm going to do pixel, if we do pix top equals, struggling with this one. Oh, cool, thank you. I will try and check that one out after the stream, I think. Right, so, sorry, where were we? We want the horizontal counter plus the vertical counter, but we need some portion of it. We can't have the whole thing. So we've got the column and the row. We can rename them later. So let's go for column 5 onwards plus row. The row is only going to be 32 as a top value, and that's only going to be 3, 4, 5 bits long. So let's go for something like 3 onwards. This is going to be a much lower resolution than the VGA monitor, so we're going to have to potentially tweak these to be counting more quickly. If we go for pix top 0, pix top 1, and pix top 2, I think that'll probably do us nicely. Let's turn the power supply back on, and let's get Glasgow up and running. Ah, there you go. We kind of got, it's not square, not at all square. Let us take the column more quickly. So I think what we want to do is take 7 bits probably. I don't know. No, I want to reduce it. Reduce it to 3 bits or 4 bits. There you go. 4 probably looks good. It'll be about twice what it is at the moment. There, squarish. Now this is interesting as well because it looks like, if you watch the scan down the panel, that here we've got an entire, I'm not sure if you can see my finger there, we've got an entire block there between those two rulers, and then another entire block, and then you've got a single row at the very bottom, which is perhaps not quite what we wanted. I think, why would that be happening? That's happening because we're displaying one row while we're clocking out the next. So actually you can see that this green up here is actually this green down here. I think it repeats at that level. So if we were to turn this off, it would go more dim, but would it be correct? Yes, it is. There you go. So currently we are probably actually bleeding between two rows. We can probably get away with this delay show because we are shifting data out for so long. If we go straight on to the reset phase, should we do that? How would that make things work? We might get the bleed again though. We probably will. That means that we get the bottom row appearing at the top of the pattern, which is not really what we want. Oh no. Oh right, whoops. Let's put that 0 in there. Yeah, we get that same issue again. So the bottom row, what should be down here, is actually appearing at the top there. Show you again. What should be appearing down here is actually coming out at the top, which is not ideal. Trying to figure out what you need to provide. Vifino are they the maintainer of SLED? And they presumably want to give it a go before they merge it mainline or something? Yeah. And you just sort of pinky promise that it works. Okay, what we can do to deal with this is use probably row -1. I think we'll perhaps take care of that issue. No, it didn't. Oh, it shifted the whole blocks along. That's, of course, what's going to happen. I'm going to leave that for now. Bottom. This is going to be row +32. +32. No, it's not. It's going to be... okay. It's row +32, but bits 3 onwards of that, which is... yes, that makes sense. And then again here, I think this is going to be row -1. -1's probably not going to work nicely. So let's leave that as just row. Oh right, I didn't wire up the pixel bottom. So px bottom btm 0. Px bottom 1. Px bottom 2. What do you reckon? Look at that. Okay, and if you look carefully, we've got the same issue happening on the bottom half. So there's actually a set of blue pixels that you can see just there, which should be appearing off the bottom of the screen here. So instead of +32, let's do +31. See how that comes out. I think that will take care of these blue pixels just here. And oh no, they've shifted further. So actually, maybe it needs to be 33 instead of 31. Come on! No! I hate this stuff. I really am not very good at thinking about this stuff. Okay, so what I've got now is the top is going to be row +1, the bottom is going to be row +33 instead of 32. Is that going to come out correct? No, of course it's not. What's happened now is that what has happened now? Oh, this. I'm not quite sure at the moment, actually. It almost looks like it's about to start a new row and it's displaying it here, which would make sense. So if we come back to here and do row -1 and row plus 31 instead of 32. Oh no, I mean, you go into computer science as a dyslexic person, you can't do maths, right? And at the beginning, you're looking at all these universities and all the courses that you want to do, and you're going, I can't do maths, I'm not allowed to do computer science, I'm not allowed to do electronics, you know. And you get there and you go, oh, it's not so bad. And then, all of a sudden, you get to things like this, where you've got zero-based counting, and you've got all this kind of stuff, which is just difficult. I cannot get my head around it. We got 2 pixels wrong now, so that's even worse. Let's put 32 plus 0. So this is just the basic. Is this perhaps... What have we actually got happening here? Trial and error for the win, definitely. And yes, I never understood. So, you know, all the way along, I was really disheartened when I was young, because I wanted to do computing, electronicsy stuff, and I knew where I wanted to go, but everyone was telling me, no, you can't do that. You can't do A-level physics without maths. I mean, come on. A quick test bench. You're probably right, actually. Although I'm not familiar enough with how the test benches work to dive into that. Check out the values in the VCD. Yeah. It's going to be quite a big dump for this, isn't it? Oh, the other issue is, of course, that the applet runs off and does its own thing, so I'm not sure we can get the values from it. How would you do that? It's not like the UART, for example, where you're interacting with it. You're still around while the applet's running. In this situation, we've set it off, and it's just gateway running by itself. Oh, you're saying to create a test bench, and with that test bench, check the VCD output. Is that what you're saying, Greg? Okay. Probably not something to do first time on stream. I'm pretty happy with that. That's a nice test pattern. It looks good. There are these issues with the first row of each half, but that's always something. And actually, if we look very, very carefully... now hang on. I wonder... So what we've got here, I'm not sure if you'll be able to see it on the camera. I'll bring it on screen. Can you see that? Just here. Maybe I have to bring it up to the camera. But I can without killing myself. Show you that one as well. The focus. So this is something that I struggled with last time I played with these panels. Was that you can see here there's this row of red LEDs which are barely on. Does that make sense? And I think that when you disable the latch, when you disable the output enable, it actually takes a little while for it to turn off properly. And so if you run the latch, or if you strobe the latch on the shift register, then the value comes out before the output enable is turned off fully. So that explains this red here, and I think we just need to delay a little bit more before we clock or strobe the latch, sorry. But the first row where we've got this bright yellow, that actually I think is much more related to here in the middle of this display. Not sure which way I need to go for focus. It'd be nice to have autofocus on this, wouldn't it? okay, they may be out of focus would help you see the colours more. Yeah, so the very first row, we've still got the bleeding between rows. You can see the red is everywhere, but the reason you can see the red is because it's after the black. I suspect the bleed is going to be on all of the other transitions as well. So let's do something about that bleed, and then we can mull that one over in terms of the first row being incorrect later, I think. Put this down again. I leave that out of focus. Does that actually look better in terms of colour than being in focus? Maybe it's not too bad. So I think, Esden, regarding the can you do that in Glasgow too, you can produce a VCD, value change dump, which you can then load into SIGROC or whatever, and you can see all of the signals and their values and when they change and everything. But the issue we've got here is that we're building the applet, loading it into the FPGA, and then letting go effectively, and the Glasgow then runs off and does its own thing. So if I show you here, when you run Glasgow with the video HUB75 output, you press go, it does its thing, and then you're back at the prompt, which means that we've got no handle onto it anymore. We can't, I don't think at this point, get VCD out. We'd have to stick around and keep it running, which might be a simple matter of just doing something in the run function, but I'm not sure. Let's I think leave that for this stream. For now, I'd like to solve the bleeding. I'm going to put some grey matter on the first row issue. So what do we do then? I think if we put an extra state in here, or an extra delay, we don't want to do the combinational on the latch until we are about to progress through. That will delay it by 1 clock. Is that going to resolve the bleed? No, it's still there. Let's do it for a couple more clocks then. Delay latch, let's make that something silly like 10. What's that going to do? Nope, still there. Have we set the... Oh, have we done that? Yeah, we have. We've set the row. Okay, so we can't run the latch at the same time we're changing the row. What we want to do in that case is put the latch high approximately halfway through and then bring it low again. Let's see if that does the job. So what we're going to end up with now is no, difficult to tell if it's improved the situation at all, but I think that's still wrong. I'm going to turn this up again so I can actually get something to focus on. No, let's turn that off. So the issue we have, your poor retinas, I'm sorry. Was it that bright? Turn it down again. Let's run it again so there's actually something to look at. Oh, that's the wrong thing to run. There you go. If the booming whatever behind me in terms of the power supply noise or whatever is annoying, let me know and I'll turn it off into a black screen every time. We've got an explanation for it, which is sometimes enough to be okay with the situation. So this bleed here, we want to turn output enable is then disabled. We get a count of 5 before we latch, and then we get another count of 5-ish before we then increment the row. So if I make this 20 and 10 instead of 5 and 10 and 5, what's that going to do? That's going to be massive. It should get dimmer at least. The whole panel should get dimmer. And it doesn't seem to. Count's not 0. Decrement the count. If the count's 10. Oh. I'm looking forward to it, Esden. It's exciting. It's been a long time coming, and I'm sure you've put so much work into it. How is it coming, by the way, or is that secret and you don't really want to talk about it? What is count? That's a 32-bit number. Yeah, so we can make that massive. Let's make that 2000. And it should maybe even start flickering and stuff. Okay, this isn't obeying us, is it? Oops. What is that going to be? That's going to be 48 megahertz. Oh, there you go. Scan lines and stuff. The issue now being, do we still get the red? It's hard to tell. You want that for visual, Esden? It's certainly scanny, or whatever you want to call it, isn't it? Looks quite smooth, actually. I like that. In terms of selling this kind of thing to people, it's so tricky. Okay, that looks fizzy, or whatever you want to call it, to the naked eye. Probably you can just about see it on camera. The bleed is completely gone now. So we've got a massive duration between disabling the output and advancing the latch and then advancing the row. So we've got 48 megahertz divided by 20,000 is that, which is 416 microseconds. Oh, sorry. That's a very good point. In terms of photosensitivity. I hope I didn't catch anyone out there. Okay, so the bleed's starting to come back in again now. Let's push this right to one side or the other and see if we can make the bleed better or worse. Difficult to tell. Let's go for 1900. Yeah, okay, let's go for 100. That's going to be optional or something, isn't it? I think we can get the latch to be really close to the next row advance, which kind of makes sense. It is bleeding still a little bit. Let's push the output enable down by half. This is kind of what I'm expecting to make a big difference. No, it wasn't too bad. Bring it down by 10. Ah, there we go. Do I need to look at this light fan controller? Let's see if we can put it there. Oh, that's not a light fan controller. Looks like a pretty beefy board though, doesn't it? Very nice. Right, in terms of this bleed, this is kind of the same sort of situation I came to previously, I think, where I just backed off quite a lot until it sort of nearly went away. I might have to speak with TNT about this and see if they've got any ideas about what to do. What is this? This is putting the output enable too close to the latch. Right, I think that'll probably just about do us. The last thing to fix up is that first line, and I think I'm going to take that some other time. Very frustrating, but there we go. Have a look here, we've actually got blue and red on at the same time, which is, yeah, it's pink, isn't it? Oh, cyan. Not cyan, it's magenta, sorry. Good with colour names too. So, okay. I think that's a pretty good state to be in for now. I think I might be starting to think about finishing the stream. Not sure if anyone's got ideas on how to fix this up or tweak it in any way. What have we got? A 1, 2, 3, 4, 5, 6, 7, 8 by 1, 2, 3, 4, 5, 6, 7, 8. A nice square, that's good. Yeah. I think that'll do for now. Hope I'm not kicking you all out. Looking at the back chat, we've got Bunny and Zobs. Are you referring to the precursor, which is the new one, which looks pretty cool? I've been watching it carefully, but I haven't actually haven't backed it or anything yet. It looks brilliant though. All of their techniques in terms of like the milling the PCB for the front panel and stuff is awesome. Omni Technolancer, yeah, this middle line and the top line are problematic, and I think I've probably covered it enough times now over and over again, but if you cut the display in half, that's effectively what we have, and this bottom magenta is then appearing at the top, and I think this is because we are clocking out a line out of phase with how we are showing it or illuminating it, whatever you want to call it. So when we are showing the first line, we're actually clocking out the second line. Oh, is it clearing the row before scanning out the next one? That's rather than the output enable being the trigger. That's a very good, interesting point. So you need to shift data, then shift blank, then move on to the next row, then shift data, shift blank, move on to the next row. Let's very quickly give that a go. let's call this blank shift, I think. Blank shift. So here we are just going to shift out zeros. Whatever. Oh, sorry, not watching the right screen. So we've added a blank shift state here. And we're just going to shift that out, then we're going to move on to the delay latch. This will, because of how we're currently running this, I think it will halve, no, it won't halve the brightness, it will just halve the refresh rate. So that's okay. Is that true? We actually need to latch it as well, don't we? So we need to latch here before shifting out a blank. I'm not going to make this full screen. Apologies if anyone's sensitive to flashes and things. That looks okay. That's the bleed is still there. Did I update everything correctly? Blank shift. Yeah, I did. Oh, for gamma. That's interesting. Okay. So when I've done this previously, I've always used the OE to actually effectively mask the latch, but I guess that's not really necessary. Sorry, mask the latch and the row advance. Here we go. So you disable the LEDs, you advance the row, and you turn the next row on. Fair enough, fair enough. We're latching here, shifting out blank. I'm going to turn the LEDs off here, but the main effect I think this will have in terms of how the bleed is controlled will be that it's off for much, much longer. Yeah, so there's no bleed anymore, but it's off. Oh, there's actually a new kind of bleed. Is that a new kind of bleed? Can't quite get my eyes in sync with this. Very bright. No, so yeah, okay. So the bleed's gone the other way now. Each of, not sure if you can see it, each of the white panels, for example, are now bleeding into the black instead of the red bleeding up into the black. So it's done it the wrong way. Anyway, let's leave it at that. I think that'll do for today. I'm going to undo that change. So we need to come down to here, I think it was. Let's just put that back on, see if it works well. Oh, I think I've seen that video probably long ago. Little tiny bit of red bleed, no white bleed, and the first row is wrong. Yes, yeah, that's a brilliant video. He describes it or explains it very well, and you suddenly go, "Oh, that's actually quite neat." Anyway, yeah, I think I won't say it again. This is going to be the last time. Thank you everybody for joining. We've got a good test pattern. There's a couple of things to fix up, but maybe that can be next week. I am hoping still to order the CAN board for the Glasgow. I haven't made the order yet, but I was just waiting to see if Electronic Eel had any comments. I think they were willing to offer some input. So I think I might order that soonish, get some bits in to try and make one of them up on stream, and then we're on to Gateware for the CAN interface, which I think that's going to be quite scary, to be honest, because there's a lot that goes on in CAN. Yes, I can push this if you like. I will point you at it after the stream has done. It's not perfect, as you can see, but it's probably good enough to show off an LED panel on your campaign. Wish you all the best with your campaign, and everybody else, thank you for joining, and I will see you soon. Okay, bye.